All right. Before we delve into project, so we have the slightly awkward thing that project 1B is still out there. Hopefully you're just done with it. If you're not done with it, hopefully you've started it. If you haven't started it, hopefully you've heard of it. If you haven't heard of it, hopefully you've now heard of it. If you haven't now heard of it, well, now I'm trapped in like a loop. Hopefully you've now heard of it. Yeah, I'm not going to keep going. But before we do that, we have to answer the question of what's the best non-sports themed movie. And so this is for future classes. We're just going to vote this time. So what's the best non-sports themed movie? Yeah. Shrek. Okay. You have all the answers, yes. The Room. Sounds creepy. Yeah. Deadpool. Oh, all right. Yeah. Spaceballs. Okay, that means you're older. Okay, yes.
Star Wars.
Star Wars. That's speaking to myself as a child. Yes, yes.
B movie.
B movie. That. Yeah. Not B movie. Yes. Lord of the Rings. Okay, LOTR, Return of King. Yeah. Yes. I said don't say anything that might get me in trouble at this university. So no shades of gray. Here we just do black and white. No gray. Yes. The Big Lebowski. Oh, okay, yeah. That kind of makes you, that's cool, right? Yeah, no, you can't get more. You get one. You can't. What's this? Which one's your best one? You already said one. You can't do two. Yeah. Blade Runner. Like the new one or the old one? No, can't pick both. It's best movie, not best movies. Okay, two more. Yeah. Shawshank Redemption. Doesn't that always get voted like the top movie? Redemption. Yes. Well, I don't get that. Okay, somebody else. Okay, over there. Okay, two more. Let's do two more. How about you? Yeah. Inglourious Bastards. Okay, I never saw that. It sounded like it's violent. Anyway, yes. One more. Oh, for God's sake. That's an old movie. Adventures of Baron Munchausen. Let's see if I can spell that right. Hausen, something like that. With an umlaut somewhere. All right, that's good enough. Now we have a set of movies which are definitely not the best movie of all time, but we will vote on them anyway. Okay, how many people vote for Shrek? Okay, 10. How many people vote for The Room? At least one. At least one people. One, thank you. That wasn't the right person. Deadpool. That looks like 11. Spaceballs. 2. What are people waiting for? Star Wars. Oh, I like it. 9. Not the B movie. Are you okay? Actually, the B movie. I don't want you voting for not the B movie. You're just doing this to troll me, but I'm going to say 0. Lord of the Rings, Return of the King. 1, 2, 3, 4, 5, 6, 7, 8. It's also kind of like 10. Big Lebowski. Nobody's voting for anything. 10. Blade Runner. 4. Shawshank Redemption. Oh, people like this. This is going to be the winner. I don't know, 15, 16. Inglourious Bastards. Oh, very interesting. Somebody raising 2 hands. That's close. I think 13. Adventures of Baron Munchausen, -2. Okay. Well, the winner is Shawshank Redemption, which is exactly like IMDb, so why ask you? Just ask the internet. This is not the best movie of all time. Okay. This, by the way, I read long before I saw. There was this is, of course, by Stephen King. There is a collection of short stories, I think all of which have been made into movies. 1 is The Shawshank Redemption. 2 is Stand By Me, yes. 3 is a very depressing movie about some Nazis. I forget what it's called. And the 4th one, I don't know if they made into a movie. Anyway, it's the book is called Seasons. Apt pupil. That's right. That was really depressing. And then the fourth one is called The Fourth Story in this otherwise fine collection of short stories. So anyway, I think it's called Seasons. Four Seasons? Is that what it's called? That's like a hotel, but maybe it's called The Four Seasons. Four Seasons. In any case, good read, a bunch of short stories, and who knew that would turn into the best movie of all time. All right, so what are we going to do? Not this. We don't have that much time left, and we will try to save your time a little bit. Like I said, we're in this slightly awkward position of not being quite done with P1B, but P1B is such the, dip your toe in the water of a kernel, a small kernel, change 5 lines of code. A lot of the XV6 projects will be like that. You're kind of looking around trying to figure out what to do, and then once you do it, you're like, that was easy. I don't even know why that was a project. So they'll have that flavor. But now we're going to be switching back to Linux world. This, unfortunately, is still done by yourself. I'm sorry. For those of you who have a dear friend whom you wish to work with, we will get to that part, but there has to be some walking on your own before we run together, and that is this part of the class. So it's good to, and also there's nothing worse than having a partner that you then rely on to do a lot of the project, because then you don't learn it yourself, right? And that happens almost naturally without anybody being at fault. If one person works at speed X, another person works at speed X over 2, the faster person does all the work and this other person doesn't learn. So we have to do some on our own to get over that. Okay, and in this part of the project, this project 2A, which isn't officially released yet, but you can, I don't know if you figured it out. I'm putting all the projects on GitHub because I want to share them. In fact, I've told you this. I'm sharing them with people so you can kind of see what projects are coming by seeing what I'm doing on GitHub and when I'm typing in project descriptions. But you shouldn't take that as official until we say it's released. But we'll release it probably tomorrow anyway, because I'm told you all like to have something hanging over your head. So I'm just here to make you happy, so you can tell all your loved ones that yes, the professor is taking care of me, making sure I always have project work to do. Rest assured, your tuition dollars are going to good use, whoever's paying them, which may even be you. What we're going to do next is a Unix Shell. Unix Shell is a great way to actually learn how this command line world works in real detail. And once you build a shell, you appreciate how cool shells are as a way of interacting with computer systems. This I'm going to get off the screen. And so what we're going to do today is learn a little bit about the shell project, and then we'll just write a little code together to start to sketch out the rudimentary a shell of a shell, I guess we could call it, a basic structure of a shell and how that works. And just like our processor, which is what? What's our processor? A while loop. A shell is very similar. It's just a while loop. And what does a shell do? It just takes your input and then figures out how to run a program based on your input most of the time. So we'll learn about that. So here's the shell description. I'll just read through it quickly with you all. So the overview is you're going to build a shell or a command line interpreter or CLI. And the shell just does that. You type in a command. A command is just a program that you wish to run. The shell doesn't actually know in general anything about that program. This is the first confusion which you should be unconfused of at this point, which is the shell. When I type ls, the shell doesn't really know what ls is doing. All it knows is it knows eventually how to find the ls binary, and then it knows how to run it. And the way it's going to run it is by creating a new process and then making that process run the program that you specified. To do that, we're going to use some very basic Unix APIs, which we'll talk about shortly. So that's the overview. And it's kind of cool just to learn how a shell works. We're going to call our shell, all shells kind of end in sh for shell. So the first shell was sh, sh, and then there was the C shell, sheesh, and then there was, the corn shell, Keish. Actually, Corn was a person, and Corn's son actually is an alum of our department. So that would have been Corn's son shell, but I don't think he ever did a shell. And then there was, there's many different shells out there today. You probably, if you don't know what shell you're using, you're probably using bash. If you do know what your shell is you're using, you're not using bash, or you are using bash. What other shells do people use? Somebody say fish. Somebody who uses fish? It's a shell. It's a real shell. A few people. Anything else? Zeesh? Z shell, yeah, Zeesh. Anything else? PowerShell, for God's sake. Okay. Yeah, when you have to say it's a PowerShell, it's not so great. In any case, there's a lot of different shells out there. And yes, we're going to be a little Unix-centric here. And so we're going to build the Wisconsin shell, Wish. And, or you're going to build it. I'm going to just grade it. And what it does is very simply you invoke it. There's actually two ways to invoke a shell. And this is pretty common, actually. They'll have an interactive mode, which is what you're used to, right? When we run a shell where we expect to type at it, and it interactively lets us do things. But we're also going to have a batch mode where you basically just give it a file of commands, and then you execute those. It executes those commands that are in that file, and then it exits when it's done. The basic loop of that is very similar. Basically, while one read inputs from either standard input or the file, and if you ever reach the end of file marker in the EOF in the standard input stream or in the file itself, you exit the shell. So the batch mode is particularly important because most of our testing will be done in batch mode. So you'll probably test it yourself by interactively playing around with it, but we will not do that exactly for testing. So both of those modes are important. When you're at a shell, you do things like this. You type, say, ls. That's all I do. I just sit here and list my files. And it's like watching your stocks, except I don't have a lot of stocks, so instead I just watch my files. And it's about as interesting. And you can see what we have here is the best non-sports themed movie, which one thing we can do with the shell is rectify errors of the past. And so now we've removed those files. And now our ls looks a lot better. So no longer do we know what the best non-sports themed movie is. We can all forget that we did that. So what is happening when I type ls? Well, one thing you notice about ls or the other program we ran, rm, a moment ago, those are binaries. And they live somewhere in the file system hierarchy. Does anyone know where they live? They live in some directory, which historically was called like bin, for example. What does bin stand for? Binary, because it's a binary executable. It's just a bunch of bits which you can load into memory and start running. And you can type which in most shells to tell you when I'm typing ls, the shell thinks I need to run this program /bin/ls. Pretty simple. Now, how does it know that? Well, that's one thing you're going to implement, which I'll talk about in a second, but it's called a search path. The search path is something that most shells have some construct like this, which basically is just a collection of directories which the shell will search through when you type a command to try to find a binary whose name matches the program that you want to run. So if I have a shell path that has /bin in it and /userbin, or maybe dot, like the current directory, which is a little dangerous to do. Some people recommend you don't do that because you might be in a directory where you don't know what binaries are in it. It would just simply search through those. Oh, it would search through. No, don't do that. Oh, hello. Yeah, I don't know what's going on. As you can tell, the mental quality, verbal quality, everything is just deteriorating rapidly. I'm just trying to get to the end of this class without dying in front of you, which would be memorable, right? You could be like, remember that class where the professor died at the end? And the last memory we gave him was the Shawshank Redemption. So anyway, so what the path does is pretty simple. It's just a place directories in the file system to look for binaries. It's simple as that. And when we find the first one, we're going to match that and use that. And it's a convenience for you. It allows you to not remember where all these programs are. Just add a bunch of directories to your path, which is just like a variable that the shell stores for you, and then look through them when you type something. So we could type which, rm, etc. These are all just separate binary programs, and you can, for example, see things about it, like how big it is and stuff like that, by typing ls on it, or you could just type ls on the directory and see a bunch of different binaries that are in there. And of course, mastering kind of any Unix shell is a little bit just knowing a lot of these little programs which can be stitched together to do things efficiently. That's something that's not easily learned. It's just learned over time through experience actually, there's nothing better than when we do partner up, if you happen to have a partner who's more familiar with something than you, that's a great way to learn, is just to see someone else doing something. I actually just wish we had more opportunities to do that with each other, because you learn so quickly how to do things efficiently when you just see somebody else do it. So many times we're not watching others. We just have to sit there and type ourselves and guess, and therefore we miss that opportunity. So we'll get a little bit of that with projects, but in general, any opportunity you have to kind of sit next to someone and watch how they're doing something. Now, that sounds like I'm encouraging copying if we're going to take it to the extreme. Don't watch what's on the screen so much, but just watch how people are, how they're doing things. And when you notice people doing things efficiently, ask them how they do it. So anyway, before we get into the paths, let's just talk about the basic path, the basic structure of our shell. We're going to use getLine to just get arbitrarily long lines of input in from either that batch file or from input. Then what we have to do is we have to parse that a little bit. So you're going to have to learn a little bit about how to split. When I say type ls-l-a, I want to run the binary ls. I want to give it and maybe on /bin, I'm giving it 3 arguments, -l for, give a little more information, do it about all files, not just non-hidden ones, and then do it on the directory /bin and show me what's in there. And what that means is I have to parse this line and figure out all the pieces of it in order to be able to call the underlying system calls that allow me to create a new process and execute this program. That's going to work, notice, with like arbitrary white space. Like if I'm a person who really likes to space things out, I could type this and the shell would go ahead and do the same thing. It doesn't complain like, why are you doing that? It just says, that's fine. Go ahead and try to hide the argument over here. The shell doesn't mind. It's no problem at all for the shell, and it won't be any problem for your shell either. ls-al, whatever. All of that kind of white space is something you're going to get rid of as you parse through a line, and we'll talk a little bit about that. Then kind of we get to the heart of what we're going to do in process creation and management, and that's through these 3 system calls: fork, exec, and then kind of a wait or wait PID system call. These allow us, fork allows us to create a new process. Exec allows us to run a specific binary in that process, and then wait allows a parent process to wait for the completion of execution of a child process. And we'll talk about a bunch of different, exec actually has a bunch of different variants. We'll talk about the one that we need to use. So that's the basic shell. We'll show a little code example in a second of that. Now I said something earlier, which is like, hey, when I'm type ls, I'm running a program, ls. Not everything you type in a shell is a new program to execute. There are these things called built-in commands. Those are things that the shell actually does itself and doesn't launch a new binary to do. In this project, you'll just have a few things which are built-ins. One is exit. Exit isn't a program you run. It's just telling the shell to call exit and end. So if I ran bash, for example, and then you can see now I'm in a different shell, and then I type ls because that's pretty exciting. Then I type exit. What the bash shell is going to do, which is just another program, is it's going to recognize that I'm typing exit and say, oh, this person wants to exit the bash shell, so they go ahead and exit, right? And I go ahead and return back to the shell that I was in at the beginning, which is my shell. And then that's a built-in command. So you're going to have to interpret that differently than, because it wouldn't make any sense to like start a new process to exit the process that you're in, right? That'd be kind of strange. You start a new process to exit, then it exits, but then just the new process exited and you're back in the shell. That's called a bug. It's not called a feature. It's a shell that you could never exit. Actually, it sounds like some strange form of hell, right? It's a shell, you just cannot exit this program. Much like the Shawshank Redemption. So I don't know what I'm talking about. So a few other things. One is changing directories. You'll learn about that a little bit detail, but changing directories is something that the shell does. We have a notion in Unix of a current working directory. So let's say I make a directory here, of course, you all know this probably, but I can change directories into it. When I do things then like ls or run lots of programs, it can assume that I'm talking about the current working directory. There's some sort of file.a or something. And you can see that file. And then when I cd up the tree with ... then I'm in a different working directory. That cd is implemented by the shell. It has a notion of where you are, and that what it does is it calls a system call chdir in order to enact that. And then path is how we're going to build that search path. You just tell it the directories to look in for a binary, and then you can go ahead and start working on it. Now, a couple of cooler features. One is redirection. We'll talk maybe a little bit about that today. Redirection is when, for example, I run a program like ls, because that's all I seem to run. And by the way, this is really terrible that I only run ls in these demos, because there will be some fraction of you that think that most of the project is just implementing ls. You are not implementing ls at all. You are just implementing something that can run any program, and I just use ls because it's such a simple example. I could use ps too, process status, right? Show us what processes are running. I could run anything. And for example, when I run ps, I might want to redirect its output to a file. So here's ps.snapshot or something like that. And what that does is it runs ps, but it creates the process in such a way that when the process calls printf, which eventually writes to standard out has been redirected to write to this file as opposed to writing to the screen. And so we can see what ps wrote, to a file here instead of in a screen. That's amazingly all done without changing anything about the PS program. And this is the beauty of Unix fork and exec, which we'll understand in some detail in a second, is that you don't have to change anything about the program you're running to redirect its output to a file as opposed to printing it on the screen. The program's unchanged. Its environment around it is changed, and that change in the environment around it is enough to allow these kind of very powerful features like redirection. So we're just going to do a little output redirection like that. There's some other couple details. And then there's one last thing we're doing. We're doing a slightly different variant of how to launch multiple commands at once. On a Unix shell, there's different ways to do this. Here we're just saying if you put an ampersand between commands and their arguments, instead of running one at a time, you're going to launch all of those at the same time. And then they are going to run at the same time. And then you wait for all of them to complete instead of just waiting for one. So that's a way to run multiple programs in your wish shell, which is a little bit different than how I would do it here. Like here I would, ps ampersand, but then I have to give it a semicolon to say, in the shell I'm using, which is the TC shell because I'm old, I run ps in the background and ls in the background at the same time, and then wait for them both to complete. And so it does both of those, and then it says they're both done. So that's how we're doing a slightly different form of that, but it's the basic same idea. Okay, and then there's one error message which you print anytime something goes wrong, and then there's just a few hints at the bottom about how to start building this up. Most people, the way to succeed on programs like this is to start simple and build things up slowly and make them work before you try to do everything. So don't try to do everything at once. And we try to say kind of some of the order that you might do this. Just kind of sketching out little working solutions to certain problems and then going from there. Okay, so any questions about the description? Kind of make sense? Okay, so let's do a little bit of code of some kind. We'll just start using the basics of fork and exec. And really, what's funny about fork and exec are they're absolutely the two strangest system calls you'll ever call. Because fork is something you call. One process calls fork, and then suddenly a new process is created, and then two processes return from fork. The parent, who created the first process, and the child both return from fork as if they were both running at that same point. So it's essentially creating a clone of the parent process. That's what fork does. It's an almost identical copy, and then you have two processes. So let's read the man page a little bit to learn a little bit more about it. Now this will look a little different than the man page you're looking at because this is on my Mac. I'm not logged into a Linux machine, but it's more or less the same. It says I should include the Unix standard header here, and then it says I should call fork with no options, no arguments, and then it returns a PID-T. The new process is an exact copy of the calling process, except for the following things. Okay, so one thing is it has a different PID. There's a bunch of other details there, and then importantly, upon successful completion, fork returns a value of 0 to the child process and returns the process ID of the child process to the parent process. That difference is hugely important, that we get a different return code. Why is that important? Why is it hugely important? Yeah. Yeah, that's right. So you can actually, in your code, do a branch based on, an if based on, hey, did I get 0? Oh, that's the child. Or did I get a non-zero? That's the parent. So let's go ahead and use code to do something here. Int rc equals fork. And like I said, right here, one process enters, 2 processes leave. I've made this every time I think about this, I think about, what do I think of? 1 process entered, 2 processes leave. Does that sound like anything? Thunderdome, exactly. Thank you. One person knows the reference to Mad Max Thunderdome. So here's our program here, main end. What is this program going to print when I run it? Yeah. Begin, then end, end. Let's try it. Yeah, nice work. Okay. Yeah, and you can see the end actually, this other end happened late after the program completed because the one program, the main program, we didn't wait for the child to complete. So you can see here what we see is we get a begin, but then we get 2 ends. That's very strange. Now let's do a little bit more here. Let's print out the return code. And now I don't have to return it anymore. And we can see that we have a difference there. So you can see in 1, we got 0. That's a child. And in the parent, we get the PID of the child. Now what we can do to confirm that even further is we can print out my PID. So let's go ahead and do that by calling getPID. Each process has a PID. And let's go ahead and look at that. Not too exciting. So let's go ahead and run this. And you can see the child's, which gets a 0 on the return code, says its PID is 51799. The parent gets the child's PID as its return code 51799, and its PID is 1 less. It's 51798. It was a slightly lower number. So that's weird, and that's what we've done so far. Now what we're going to do is a pretty common thing. If RC equals 0, what we're going to do is, as we remember when we look at the man fork page, man of fork, we get a value of 0 in the child, right? So we're going to write code that says, oh, this is the child. And when you're in a shell that you're creating, you're going to be, whenever I say type ls, I'm generally going to be, if it's not a built-in command, I'm going to be creating a new process, and then on the child side of the code, I'm going to be figuring out how to run ls. And in the parent side, generally what I'm going to do is I'm simply going to wait for that process to stop running. So we'll talk about how to do that. So now here we're going to print out I'm the child, and children yell a lot, so we'll make it exclamations. And otherwise, I'm the parent, and what do parents do? They just patiently wait for the child. And so how do we wait in Unix systems? Well, let's go ahead and look at the wait system call. There's a bunch of those, but we'll just use simple wait here. And let's read about that. The wait function suspends execution of its calling process until some information is available about a terminated child process, which sounds very sad, actually. Sorry to inform you, the child process has been terminated. The parent can stop waiting. So, and on a successful call, this argument that you've passed in contains some information about that process. In fact, that's how you can get like the return code of a child process you ran. We're going to kind of ignore that for now. And then what we're going to just look at here is what is returned. If it returns, the process ID of the child is returned, otherwise -1. So either we can just go ahead and look at it and see what it is. Else we'll say RC equals, let's say int wait, and let's do that. We don't really care about filling in that information. And then what we'll do is we'll print out something here, parent done waiting for what? Terminated child process. Very sad, sad. So that's what's going on here, and we're going to go ahead and run this program. So what this program, let's go ahead and remove this. What is this program going to print? Well, if we didn't have this wait, what could we say about what's going to get printed on the screen? We know that main begin gets printed first, but then we call fork, and now we have a parent process and a child process. Now, what do we know already about the operating system and what it might do at this point? Well, there's a scheduler, and it might decide if there were only one CPU, it might decide to run the parent. It might decide to run the child. So if the parent isn't waiting for the child, we don't know if it would print child then parent or parent then child. But once we put this wait in here, what we know is that when we call fork, then the child gets created. There are two runnable processes, but if we happen to run the parent first, it's going to go into wait, and this is one of those things that blocks the parent until the child is done. So that means if we're thinking in the terms of what we learned in lecture, wait goes into the kernel and basically tells the scheduler, I'm no longer runnable. I'm now blocked. And what I'm blocked on is that child process terminating. And when that child process terminates, unblock me and make me runnable again, and then return from wait and tell me some information about that child. In the meanwhile, the child will eventually run. Whether it runs first or second, it'll eventually run print child, and then the parent will be done waiting. So let's see if we did that correctly. Did I do everything right? No. What did I miss? Yes. Okay, so that's deterministic. And if we don't believe me, we can put a sleep in here. Children are often sleeping. I've also learned that in years of parenting. We could go ahead and call sleep. Sorry, it's not in section 2. It's in what, 3? Do we have this already? It just sleep. What sleep does is basically put a process to sleep. Yeah, we already have this. And basically block until some timer goes off. In this case, 10 seconds later. So now what will happen is when we run this program, of course, is main begins. The child is created, and just like children actually do in the real world, right when they're born, they sleep for a long time. Then they wake up and they scream, and then the parent's done waiting for now the terminated child process. Grim world. You're alive. You're dead. So that's that grim world. So now we have some understanding of how fork gets called. It's the strangest thing, and your shell is going to be doing this repeatedly for programs. And let me go another 8 minutes, and we'll get enough of this that you can get a sense of how to implement this project. But this is not very interesting because the child here, first of all, is just dying right away, and it's sleeping, so let's get rid of that. But you notice the shell isn't just running copies of itself. That doesn't make a lot of sense because running a copy of yourself, it would just make more shells, and you'd probably stop using the computer eventually. Like if everything you typed just ran another shell. You could do that. I mean, for a while it's exciting. Like you're like, okay, bash. Oh, that's awesome. I love bash. And then, oh, maybe zeesh. Oh, this is pretty sweet. And then what else do I have on here? Do I have K-shell? Yeah, boom. That's a dollar. It's a dollar sign. And then who knows? Let's run seesh. Yeah. And then sh. Why not? And the list goes on. Is fish installed? No. And the command not found. PowerShell. Come on. So anyway, let's back out of all of those. And eventually we get back to my shell. But that's not as exciting as that demo just was. Actually, the demo was pretty good, wasn't it? It's like, hey, there's all these shells on here. And by the way, just learning one shell, you just should pick one. Whatever that one is, talk to your friends, look up what's the best shell on the internet. And it's really valuable. If you want to be a good programmer in the C Unix world, you have to be good at the shell, and it's fun to be good at the shell. You can do really powerful things, including write shell scripts. So in any case, But what we generally don't want to do is something more than that. And to do that, we're going to have to use some variant of what's called the exec system call. So you can see on the Mac, sorry, there are a bunch of variants. We'll use one, exec v. And let's just look at that. And it takes a path, and then it takes an argv array. Okay, so this is going to be, if you have to know how to create an argv array properly. And why do we need that? Because we're going to run a new program, and we're going to give it all its arguments, right? And that's how it's going to say ls, and the first argument is -l, and the second argument is -a, and the third argument is -temp or whatever. So we have to create all those things. So let's go ahead and cut and paste this, and then we'll read about it. Oh, sorry. Then we'll read about it. But that's what generally we're going to do in here. We need to somehow call execv to run a new program. That's what's going on. So let's read the man page in order to see what it says, what execv does. Well, what it says is the exec family of functions replaces the current process image with a new process image. They're all front ends for execv, and initial argument is whatever. So what does that mean? It means that the child process here is running as the shell. So when you first call fork here, you used to have one shell. Now we have two shells, if this is our shell here. Or really it's just main, but eventually it's going to be our shell. So now we have two processes of the shell, but we want the child to transform itself. Because right now, what's in the child address space? It's the code of the shell and the heap of the shell, a copy of the heap of the shell and a copy of the stack of the shell. But it's a complete copy of the address space of that shell. We don't want that address space anymore. We want to run a new program. That new program we're going to get by specifying it here to execv. And when we call into execv, well, remember, it's kind of the opposite of what fork does. Fork, we call once, and it returns twice. Execv, we call once, and if we're successful, how many times does it return? 0 times. Execv, when successful, never returns. Because what it does is it loads a new program binary into the code part of your address space, initializes some data, creates a new stack and heap for you, not the old one that the shell was using, and then starts running that program at main, right? The first instruction of your main program. So that's what it's going to do. Very simple. So in fact, let's go ahead and see that happen. Now for us to use this, though, we have to construct this path in argv correctly. And so let's talk a little bit about how to do that. First, we'll just kind of create a my argv array or something like that, and I'll just make it large. Now, my argv 0 equals the name of the binary that I'm going to be interested in. And so I'm going to use a function called string dupe for this, or the old string dupe, which is going to take a string that I pass it, like a static string, create memory for that string, and then pass me back a pointer to that. I'm going to have to include string.h to do that. This is not exactly how you will do this, because you'll be, instead of always running ls, which I warned you I'm always going to run during this demo, you're of course going to be parsing the input that the user types and turning it into the program that they run. So I'm going to go ahead and call string dupe and then say I want to run bin ls. And let's say I want to pass an argument to that. So let's go ahead and call string dupe and then do -l. And then critically, when you're setting this up, not that you necessarily know this, we have to know when argv, notice we don't say how many entries argv has. So the way we know the end of the argv array is we make the next one null. This is important. If you don't do this, your program will have the behavior of all frustrating C programs, which is what? No, sometimes it will work, and then sometimes it will segfault. Because sometimes it'll just be that a null, which is just 0, will be in the right place, and your program will work. And then you'll tell me, well, I just changed one thing, and then it didn't work. I think the compiler's broken. I just changed one thing, and it didn't work. I think it's that meltdown bug that you keep talking about. Not true. It's almost always you. Once in a while, it's not. I mean, amazingly, you'll eventually work somewhere where you will discover, or someone will discover, a processor bug, which just happened, or a compiler bug. That absolutely does happen. But most of the time, we should accept that we are fallible, more so than the compiler. So now we just have to pass these args correctly to this thing. Let's see if I can do that. it's a little bit redundant because remember when we looked at man for exec, it told us that execv takes the path to the full path to the binary, and then argv0 through whatever, which include argv0 is the path to the binary. So it's a little bit redundant. But if we did this correctly, what this will do now is in the child, print child, and then set this thing up, and then overlay that running process with this brand new thing and execute it. So let's see if I did that correctly. Probably not. And you can see what happened. The main began, the child began running, the parents just waiting, and then suddenly we see the output of our favorite program, ls. We could, of course, run some other program, main2.c. Let's say we did that real quick. We could print something in here, main2 rules, which is not very exciting. And then we could, of course, do that. And we could run that out here. But we could also go ahead and inside of this other program just run .main2, and we can pass an argument because main2 is a pretty simple program. It doesn't mind being passed lots of arguments. Arg to main2, which is ignored. But anyway, why am I typing this? So let's go ahead and compile that, and then we could, of course, run main again. And you can see inside of here main2 rules, because that's what we did. We ran exec, and we see in this main program, which is our shell eventually, it's nothing happens here. We could print something here. In fact, you should print a printf here because what this means is exec failed. This is a really good way to check is exec failing. And, for example, I can see if this causes a problem like I claimed when I don't null terminate it. It might not. Exec failed. It did in this case. So you can see that's nice. And then you see when we get that correctly, do it correct, we get main2 rules again, which is already becoming tiresome as a message. So that's fork and exec. Quickly, I want to do one more thing. I have 2 minutes. Any questions? Okay, I actually don't want to do one more thing. I would want to do one more thing. Okay, let me give me 1 minute, okay? 1 minute. Here's the thing I want to do. There is, if we look at, this is going to be a little bit hackish. You know what? I'll do this later. I don't want to do it in a way that's bad. Let me just explain what I want to do. We'll do it later. What you can do, if you want to redirect the output of, say, main2 in this case, to a file, all you do is you have to close the standard output, which already exists. And when I call printf, eventually it writes the standard output, which is just an open file descriptor. If I close that and then I open a file, the file I want to redirect to, the process then, when it runs, simply writes to that file. It's as simple as that. That's all redirection is. We'll talk more about it later. Okay, thank you for your patience.